Controlled Environment Plant Production Engineering Technology Education modules are developed and presented by The Ohio State University, Rutgers, the State University of New Jersey, and the University of Arizona, with support from USDA NEFA through their Higher Education Challenge Grant Program. In this module, we will discuss the topic of environmental control strategies. This module is presented by Dr. Peter Ling of The Ohio State University and Dr. A.J. Both of Rutgers, the State University of New Jersey. This Environmental Control Strategies module will allow you to meet 4 objectives. By the end of this module, you will be able to describe control systems and their basic components, list environmental parameters and interactions important to plant production, understand performance of control strategies for a single set point, and adjust set points based on environmental parameters. The first objective is to describe control systems and their basic components. Control systems can be either open loop or closed loop. In an open loop control system, control actions occur based on the current state of the system. The discussion following focuses on environmental control applications. Open loop controllers are simply programmed to take action. They do not monitor the environment around them to see if action is required. For example, simple and low-cost timers can be used as an open loop control. A timer runs on and off control actions such as supplemental lighting at programmed times. A timer cannot decide to keep supplemental lighting on during a cloudy day. A timer controlling irrigation will water plants regardless of how moist the soil is at the specified time. If soil is very moist and the irrigation timer kicks the water on, the plants will be overwatered. On the other hand, if plants are drying out quickly, the timer will not kick on until the pre-specified time, causing drought stress. These issues can be corrected with a closed-loop controller. With a closed-loop controller, control actions occur based on observed changes in the current state of the system. For example, instead of controlling supplemental lighting with a timer, the lighting could be controlled with a light sensor. A controller would be programmed to turn the lights on not only at specified times of day, but also when light level is below a specified threshold. An irrigation system could be connected to a soil moisture sensor. Rather than turning the water on at specified times, the water could be turned on only when soil moisture drops below a specified threshold that has been programmed into the controller. In this module, we will focus on the closed-loop controller. 2 types of closed-loop control systems exist. First, there is the direct controller. The direct controller responds to locally detected needs. For example, greenhouse temperature rises and a vent is opened. There is also the indirect controller. The indirect controller responds to outside conditions that will affect the local conditions in the greenhouse in the near future. For example, in the morning, outside temperature begins to rise, and the vent is opened before internal temperatures have a chance to deviate from the set point temperature. For closed-loop control, we have briefly described that there is a sensor detecting the environmental condition and a controller that has been programmed. Let's have a quick look at how the parts of this closed-loop system are connected. The system is composed of the controller, actuators, such as motors, pumps, and heating devices, the greenhouse, where environmental processes occur, and sensors, such as devices that measure temperature, humidity, and light level. For example, if this system is controlling humidity, the controller would be programmed with humidity set points. Sensors send humidity data to the controller. When humidity in the greenhouse deviates from set point by rising too high, the controller activates corrective equipment such as ventilation fans. Dropping humidity in the greenhouse is monitored by those relative humidity sensors. Sensors send humidity information to the controller. The controller then turns off the ventilation fans when the humidity has reached set point. For more information on the hardware composing the control loop, see the Data Acquisition and Control module. The second objective is to list environmental parameters and interactions important to plant production. Control over the following parameters is important in controlled environment plant production: light, carbon dioxide, humidity, temperature, air movement, and root zone. This list includes many major environmental parameters, but it is not exhaustive. Control systems that maintain specific environmental variables are beneficial. As an example, let's look at how specific control of temperature is beneficial. The ability to specifically control temperature will lead to higher quality crops. Wendt summarized many research papers on plant growth and temperature. Although this paper is from 1952, it shows that there are multiple examples of plant species that have optimal growing temperatures at different stages of growth and development. A control system capable of keeping a specific temperature will conserve resources such as fuel. A narrow temperature range keeps optimal temperature without overheating. Imagine a control system where temperature oscillates several degrees above and below a set point. This is not uncommon in a greenhouse. A grower may ensure that optimal temperature is satisfied at all times by setting the thermostat several degrees above optimal. This choice ensures that temperature does not drop below optimum, but the temperature may at times be many degrees above set point. In this scenario, in the winter, overheating exacerbates heat loss through the greenhouse structure. In this module, we will study what are called on-off controllers, and then alternatives to on-off controllers. As you view this module, keep in mind that the alternatives to on-off control are designed to smooth out climate fluctuations in the greenhouse and therefore achieve more efficient crop production. Objective 3 is to understand the performance of control strategies for a single set point. We will start with on-off control. In on-off control, the corrective equipment is either fully activated or fully deactivated based on a set point. The key of on-off control is that the piece of corrective equipment is either full power on or off. We will visualize on-off control using the graph at the bottom half of the screen. This graph will represent on-off control of a greenhouse heater. Temperature is on the y-axis and time is on the x-axis. The set point temperature is marked on the graph. Above the set point temperature, the heater is off. This area is shaded blue. Below the set point temperature, the heater is on and the graph is shaded red. We initially turn the heater on when the greenhouse is cold. The heater remains on until set point is reached, but there is overshoot, then undershoot, then overshoot, and the cycle continues. As you can see, there is a great deal of temperature oscillation. While on-off control works, it will not maintain a stable temperature. So the disadvantages here are large environmental fluctuations due to delay between a corrective and measuring equipment. The control measure, in this case the heater, may be too much. It could also occur that the control measure may be insufficient and it is impossible to reach set point. Also, rapid on-off cycling can lead to excessive wear on equipment. Equipment wear due to on-off control shortens equipment life. Some examples include shade screens wearing out with excessive opening and closing, and the shortening of the life of a lamp, for example a high-pressure sodium growth light, by turning it on and off frequently. In addition to shortened equipment life, unwanted pollutants are produced from incomplete combustion when a furnace is turned on from being cold. On-off control can lead to boiler shock. Boiler shock is when the return water is coming back to the boiler at a relatively low temperature. This temperature difference, with the hot boiler and its contents, can create significant stresses on the boiler components and may result in premature failure. The solution is to incorporate a way to control the temperature of the return water. On-off control typically does not allow for fine control, such as regulating the water temperature. We typically use mixing valves for this purpose, and they need proportional control at a minimum. There are methods for reducing equipment wear with less frequent on-off control actions. These methods include the time delay, deadband, and averaging measurements. In the next few slides, we will talk in more detail about each of these three methods. The time delay requires equipment to run for a minimum amount of time, even if the set point has been reached. On the flip side, the time delay also requires a minimum amount of off time. HID lamps, such as high-pressure sodium and metal halide, require a minimum amount of off time. The deadband is a buffer programmed around the set point. We will explain using a temperature control example. In this example, we will have a set point of 20 degrees Celsius and a deadband of 1 degree Celsius. This deadband could also be described as plus or minus 0.5 degrees Celsius. The image below represents this deadband. Temperature will drop below 20 degrees Celsius, but the heater will not turn on until 19.5 degrees Celsius. Once the temperature has reached 19.5 degrees Celsius and the heater turns off, the temperature may rise above the set point temperature of 20 degrees Celsius, but the cooling system will not turn on until 20.5 degrees Celsius. The deadband saves energy and reduces equipment wear. The larger the deadband, the more energy saved and the less equipment will turn on and off. The deadband does increase temperature oscillation. The smaller the deadband, the more stable internal temperature will be. A grower must balance energy use and equipment wear with climate stability. If average measurements are used for control, cycling is reduced. Measured values can vary from 1 minute to the next. If measured values are used directly for control, the resulting control can be erratic. Instead, computers can measure more frequently, once a minute for example, and use an average, calculated over several minutes, for the control. As an example, the graph below shows the opening and closing of a shade curtain based on the measured value of light level. Light level is on the y-axis and time is on the x-axis. When light level is in the red region, the shade is open. When the light level is in the blue region, the shade curtain is closed. The blue line represents 1 minute interval measurements, and the red line represents 5-minute averages. When the line crosses between blue and red regions, the shade curtain is moved. As you can see, it was necessary to move the shade curtain 9 times using the 1 minute interval measurements. Using 5-minute averages required only a single curtain movement. Other parameters, for which we often use the method of using averages for control purposes, are wind speed and wind direction. On this slide, we will introduce a more advanced way of working with corrective equipment in an on-off fashion. This method is called multi-stage control. When it is critical that environmental set points are maintained, often successive control measures are implemented. Alternatively stated, as the environmental condition deviates further from set points, additional control measures are activated. Let's walk through an example with a cooling system. This example will be a 4-stage approach as 4 successive control measures are used. Temperature rises past the set point and a vent is opened. This is the first stage. Temperature continues to rise and a ventilation fan turns on. This is a second stage. The second stage increases the cooling capacity of the greenhouse. By increasing cooling capacity as the demand for cooling increases, we can smooth out the temperature oscillations from a one-stage on-off control system. If temperature continues to rise, a second fan turns on. This is the third stage. If temperature keeps rising, a cooling pad gets turned on for a fourth and final stage. Let's put some numbers to this example. Stage 1 might be programmed to initiate at 3 degrees over set point. Additional stages might activate at 2-degree increases in temperature. Stages should be activated in order of increasing cost. Stage 1 has the lowest operating cost, Stage 2 has the second lowest cost, and the final stage is the most costly to operate. We are now moving beyond simple on-off control. In this slide, we are introducing proportional control. As a parameter further deviates from the set point value, the strength of a single control measure is increased. Let us use a variable speed exhaust fan as an example. As the temperature continues to deviate further from the set point, the fan speed is steadily increased. In this example, the control system is able to smooth out fluctuations that would have been the result of a multi-stage on-off control system. Here we will visually compare on-off control with proportional control. You have seen the graph of on-off heater operation before. You can see the oscillation in temperature about the set point as the heater is turned on and off. A deadband or a time delay can prevent equipment from cycling on and off as fast, but may increase environmental oscillation. Data averaging does a good job of reducing on-off cycling without necessarily increasing oscillation, but will not eliminate oscillation. Multi-stage control will do a better job smoothing out oscillation, but will not eliminate it completely, as turning on and off additional control measures will cause sudden fluctuations. So let's see how proportional control works to smooth out oscillation. The graph is a little bit different. We can still see how above the set point the heater is turned off. But when the heater turns on just below set point, it is not at full power. The farther below set point, the higher power the heater will operate with. So let's turn the heater on when the greenhouse is cold. The heater starts at full power but reduces closer to set point. Therefore, the overshoot is not so bad. On again at minimal power, small overshoot, and so on until the oscillation nearly disappears. It is important to note that with certain controllers, there are ways to make corrective equipment that is simply on or off work to do proportional control. How does proportional control work? A specific deviation from a set point is aligned to a control response. We will explain with an example for passive ventilation. Let's say the set temperature is 20 degrees Celsius. At 25 degrees Celsius, the vents will be 100% open. The maximum deviation in this case is 5 degrees Celsius. The 5 degrees is known as the proportional band, or the P-band in short. Maximum control response in this case is when the vent is open 100%. So, every 1 degree Celsius above 20 degrees Celsius, the vents will be opened an additional 20%. Note that the user specifies the size of the P-band and that the control system then applies a linear response. This table is a continuation of our proportional control example with ventilation and a 5 degrees Celsius proportional band, or P-band in short. On this chart, you can see the set temperature is 20 degrees Celsius. On the next line is the actual or measured temperature. Third line down is the temperature deviation that was obtained by subtracting the set temperature from the actual temperature. On the bottom line is the percent of vent opening. At 0 degrees deviation, the vents are fully closed. At 1 degree, they are 20% open. At 2 degrees, 40% open, and so on. At 5 degrees above set point and beyond, the vents are fully open. The P-band is the range over which the magnitude of the control action is adjusted. For the 5 degrees Celsius P-band, the vents opened by an additional 20% every 1 degree Celsius above set point. If the P band is increased to 10 degrees Celsius, the vents will be opened by an additional 10% for every 1 degree Celsius temperature increase above the set point. On this slide, we have two tables comparing the 5 degree and 10 degree P bands. With the 10 degree P band, the vents will open with smaller step sizes. Let's continue discussing the finer points of proportional control using the ventilation example. During the winter, when heat and water vapor can be removed quickly, a larger P band ensures smoother control. In summer, when heat and water vapor cannot be removed so easily, a larger P band will work too slowly, and a smaller P band is more appropriate. The graph represents how ventilation P band might be adjusted to account for outside temperature. This graph is used to visualize the idea that P bands may need to change as environmental conditions change. The P band that works best for a specific greenhouse at a given temperature may be different than that shown here. In many cases, more than one environmental factor impacts the appropriate size of the P band. For example, wind can also have an impact on the effectiveness of the ventilation system. Assuming higher wind speed has a positive effect on ventilation rate, increased wind speed allows for a larger P band. The graph shown here demonstrates how the P band can be adjusted not only by outdoor temperature, but also by outdoor wind velocity. Let's discuss a limitation of proportional control. To describe a problem that can occur when using proportional control, we will discuss the 5 degrees Celsius P band used to control vent opening. Set point temperature in the greenhouse is 20 degrees Celsius. At 12:59, the greenhouse is at 25 degrees Celsius, and so the vents are fully open. At 1300 hours, the temperature drops to 24 degrees Celsius, and the vents close by 20%. The 80% vent opening is just enough to prevent further temperature rise. However, in this case, the 80% is insufficient to return the greenhouse to its set point temperature. As you can see from the graph, proportional control is not working. Temperature has not deviated enough to change the vent position, but the vent position is insufficient to return the temperature to the set point. Is there a solution to this problem? Yes, there is a solution. The problem can be solved using proportional integral, or PI, control. If the measured value differs from the set point by a certain amount over a specific amount of time, the control system changes its response by a few percent after a specified amount of time. There are other more advanced control strategies that can be used to further improve control performance, including PID, or proportional integral derivative control. PID won't be discussed further in this module. On this slide, we will move on to discuss the indirect or anticipatory control that was mentioned at the beginning of this module. Anticipatory control initiates control actions before local conditions start to deviate from the set points. Let's recall the example verbally touched on at the start of the module. A weather station is often used to help determine the necessary control measures. If in the morning the outside temperature rises, the computer could open the vents before the greenhouse temperature starts to increase. Or, in the late afternoon when outside temperature drops, the computer could start the heating system before the greenhouse's inside temperature starts to drop. Anticipatory control reduces potential parameter fluctuations. We have finished Objective 3. Objective 4 is to adapt set points based on environmental parameters. The goal of any controlled environment plant production is to maximize the rate of photosynthesis. Parameters that contribute to the photosynthetic rate are light, temperature, and carbon dioxide. The rate of photosynthesis is limited by the values for these three parameters as shown on the chart below. The chart shows light, temperature, and carbon dioxide ranging from poor to minimal. Photosynthesis, represented by the green bar farthest to the right, can only be as great as the least optimal environmental parameter. This environmental parameter, at the least optimal level, is the limiting factor for photosynthesis. As shown in this particular chart, the limiting factor is light. Let's look at some examples. Please keep in mind that the numbers provided in these examples are not backed up by research. They are simply listed to explain the concept, as the numbers will be different depending on specific crops. As one parameter value increases from suboptimal to optimal, other parameter set points should be changed in order for them not to become the limiting factor. First, we will examine how light and carbon dioxide interact. The amount of CO2 that a plant uses during photosynthesis is dependent on available light. The table at the bottom demonstrates that as light level increases, the amount of CO2 maintained in the greenhouse should be increased. This way, CO2 does not become a limiting factor on sunny days. Conversely, CO2 is not wasted in the greenhouse on cloudy days when light is a limiting factor. Now let's examine how light and temperature interact. It is unnecessary to maintain high temperatures when light level is suboptimal. Higher temperatures encourage growth, but as a result of lower light intensities, the plant is not able to sustain a high rate of photosynthesis. The result is a weak plant. The table at the bottom is similar to the one on the previous slide. However, this one demonstrates how temperature set point should be lowered as light level is decreased. There are other interactions to consider. Temperature and carbon dioxide affect each other through the rate of photosynthesis. Looking beyond photosynthetic efficiency, there are other set points that may be changed. Vent and heat dehumidification operations should be terminated when outside humidity is high. When outdoor humidity is high, running vent and heat will only waste energy, and it will not achieve the relative humidity set point. By adjusting set points for photosynthetic efficiency, energy can be saved. On the graph below, you can see the wasted energy on temperature control and the wasted energy on CO2. Alternatively, photosynthesis can be enhanced. We can supplement lighting to take advantage of good temperature and CO2 levels. Boosting light level will boost photosynthesis. Thank you for viewing.